Hello everyone. Today module 3 will be started. So in this module 3 we will discuss about transient behavior and initial condition. Number 3, transient behavior and initial conditions are studied. That means a behavior of the circuit elements under switching conditions and their representation. Evolution of the initial and final conditions in RL, RC and RLC circuits for AC and DC excitations. After discussion these two topics, we will solve numerous problems on the module number 3. So before continuing the module number 3, so the third module, initial and final conditions. Most of the transmission lines, electrical circuits and communication networks are made up of network elements like resistors, inductors and the capacitors. These networks are connected by voltage source and the current sources. It is most useful to understand the behavior of the network when we switch on the network by supplying the voltage source. For example, we have said communication, transmission lines, electrical circuits, they have passive elements like R, L, C. They are interconnected, and when the voltage source or current source, they are connected to that network through a switch. This is the representation of the switch. Switch can be represented in this fashion. It is what? Switch. Or else it can be represented in this fashion. What is the meaning of these inward and outward arrow? This is the representation. This is the one more representation. Meaning of this first switch is when time is equals to 0, switch is closed. That is the meaning of it. When switch is operated, it will be closed. That is the meaning of this term. When switch is operated, it is open. That is the meaning of this. Alright. So let us consider the first case. Okay. Can we call two conditions before switching and after switching? You know what do you mean by switch? What do you mean by switching? When button is there, when it may be turned on and it may be turned off. Just like the switches available in your home. When it is pressed, light is on. When it is pressed once again, the light is off. That pressing operation is called as a switching here. So consider this symbol. When that switch is not pressed. So if this is the case, means before switching it was open. Is that like this? When switch is not operated, when switch is not used, before acting on the switch, what is the condition? Its condition is open. Alright? When switch is pressed, when switch is operated, after switching, it is closed. Is that equivalent circuit representation? Equivalent circuit representation after and before switching. Is that okay? Consider the one more possibility. It is a switch, but this is the direction and they have given this as 0. Meaning of this is before switching, because of this direction, when this switch is operated, actually it opens. You see the arrow direction here. At time t is equals to 0, switch is operated. When switch is operated, this switch will go to this position from this position. Meaning of this is, before switching it was closed. Before switching it was closed. When this switch is pressed, after switching it will be open. You should know this concept very properly. The whole topic depends on this concept only. Do you have any doubt? Consider a normal fan. Consider fan. It is connected to the voltage source. In between that, the switch is connected. So consider the simple analogy. A fan. This fan is connected to voltage, and here a switch. Usually that switch will be like this in your home. Okay, so here you may write on, here you may write off. Okay, so this is what and representation of a switch here. Okay, so such thing is considered here. For example, and I have said this is what the first representation of the switch. It is what 0. In that case, so consider this condition when t is equals to 0. The meaning of this is, at a time t is equals to 0, or else at a time t is equals to 0, when switch is operated, switch will be closed. That is the meaning of this. Means that when you do press this switch, what is this operation? It acts as a closed circuit. Is that right? Alright, the same condition is considered here. So when this symbol is used, when switch is operated, it is closed. So fan start running. Alright. Then when switch is not pressed, means that, so fan is connected, voltage source is available, switch is not operated. Meaning of this is what? Switch is open, fan will not be running because there is no closed circuit, there is no flow of the current. It is open. Means that it is before switching, it is after switching. Alright, let us consider the one more case. The switch symbol is used like this. Meaning of this is your switch is already closed. The meaning of this is switch is already closed. When it is operated, it opens. Meaning of this symbol. So initially it is already closed. Initially it is in this state. Okay. So first thing, then once it is pressed, what happens there? It acts as open, obviously. Initially it was closed, so that fan was running. When it is operated, when it is operated, because of this symbol it opens, so that fan will stop. What is the condition of the switch before operating? Before operating, if this is a symbol, what was the condition? It was closed. Is that okay? Have you understood the operation of these symbols? Have you understood? All right. So you should think your switches available in your home. They do perform two operations. Either they are closed or they are open. Keep that point in your mind. When they are not operated, they do maintain their previous state. When they are operated, they do change its state. This is a simple concept. I repeat, consider your switches available in your home. When they are not disturbed, when they are not operated, they do maintain their previous states. Either they are closed or open, the same state will be maintained. When they are operated, when they are disturbed, then they do change their state. If they are closed, they will be open. If they are open, they will be closed. This is what I wanted to say. All right. So next thing is, assuming that at a reference time t is equals to 0, switch in the circuit is closed, and also assuming that switch acts in 0 time, means that it is what state, it is what off, it is what on. What we are assuming, there is no transition delay. Switching happens at a t is equals to 0 seconds. No wastage of time while shifting from one state to another state. That is said here. Alright? To differentiate between the immediately before and immediately after the operation of the switch, t is equals to 0 minus and t is equals to 0 plus signs are used. It is the important concept here. Means when we do say that t is equals to 0 minus, when we do say that t is equals to 0 plus, you should use the words immediately. Immediately before switching, they are always called as t is equals to 0 minus, or else it is what t 0 minus. Many symbols can be used here, right? T is equals to 0 minus, or else t in the bracket 0 minus, and so on. Means that immediately before switching, if this waveform is viewed telescopically, what happens then? Actually, we do find some variation between two states, on and off. Again, if it is zoomed properly, we do get some disturbance here, on, off, on. So the same waveform is viewed telescopically. So microscopically, if they are used, you do find some variations between these two states here, on and off. So if we do say that this is t is equals to 0, if this is t is equals to 0, this portion is called as immediately before switching. This portion is called as here t is equals to 0 minus. This portion is called as here immediately after switching. Means that these two time intervals are measured in terms of milli or even microseconds. or even in nanoseconds. Keep that point in your mind. We are talking this immediately before and after switching concepts. Those timing intervals are related to milliseconds or even in the nanoseconds. So all these operations consumes very less time intervals. We are studying that concepts in the initial and final conditions theorem. Alright, I hope you have got the idea about what you mean by t is equals to 0 minus and t is equals to 0 plus. T is equals to 0 minus means what happens immediately before switching. T is equals to 0 plus means what happens immediately after switching. Keep that point in your mind. Alright, now so if we do measures the parameters immediately before switching, all are denoted as t is equals to 0 minus, v is equals to 0 minus and charge q minus. Keep that point in our mind. So actually it is current, it is voltage and it is charge. It is measured immediately before switching. That's why it is represented as I0 minus, V0 minus, Q0 minus. The condition existing immediately after closing of the switch is denoted as t is equals to 0 plus or even t is equals to 0 plus. It is a suffix is used here. Suffix or prefix, you can get this value. So t is equals to 0 plus. So these are the two different notations. So these are the different notations. They are calculated. They are known as the time interval immediately after switching. Immediately after switching. So that initial conditions of the network depend on the fast history of the network prior to the closing of the network at t is equals to 0 minus and the network structure at t is equals to 0 plus after the switching. You can see here. So initial condition of a network depends on two factors here. The first factor is what was the status before switching, what will be the status after switching. So these two contributions will decide the initial conditions of the network. I repeat, initial conditions of the network depends on two factors: the behavior of the network before switching, behavior of the network after switching. By combining those two characters, we can decide the initial condition of any network, right? And you can see here. So what do you mean by I0 plus, V0 plus and Q0 plus? These are the currents, voltages and charges calculated immediately after switching. These are the values calculated immediately before a switching. You can see here. Immediately before switching, immediately after switching. Am I clear? Have you understood the meaning of these symbols? T is equals to 0 minus, T is equals to 0 plus. What is the difference between I0 plus, I0 minus, V0 plus, V0 minus, Q0 plus, Q0 minus? Good. So, definition: the evaluation of the voltages and the currents and the derivatives at t is equals to 0 plus are known as initial conditions. We have discussed this definition properly. The evolution of the voltages and the currents and the derivatives at t is equals to 0 plus, we know immediately after switching, they are called as initial conditions. Evolution of the conditions at t is equals to infinity are known as the final conditions. So what is the meaning of this? T is equals to infinity. So maintaining the status of the switch for the long period of time, that is called as t is equals to infinity here. So I will say here, let us consider the same fan example. Here voltage is applied, here switch, t is equals to 0. So before switching, fan was off because it was open. After switching, After switching, so before switching, fan was off. Before switching, fan was off because switch was open. Okay. After switching, fan start rotating because closed. What happens at t is equals to infinity? If the switch is maintained, in on condition for a long time interval, that is called as a final condition here. Hopefully you have understood it. So before switching, after switching, and t is equals to infinity. So immediately after switching, do you say that fan will be rotating at its rated speed? When switch is pressed, when switch is operated, do you say that the fan will be running at its rated speed? No, it is not possible. So that if we say, we know the meaning of t is equals to 0 minus and t is equals to 0 plus, they are measured in terms of micro, milli and even in nanoseconds. So immediately switching, and after, before and after switching, you can say that fan is even off condition, because to get its speed it takes some amount of time, but we are talking about in terms of milliseconds. So we are talking in terms of milli, micro and nanoseconds. So if that is the case, means immediately before and after switching, fan is off. That will be discussed later. Okay, so I wanted to say the meaning of this t is equals to infinity if switch is maintained its state for a long time interval. So that is called as here the final conditions. That is called as here the final conditions. So what is the need of studying of initial and final conditions? Means objectives of this studying the behavior of the circuits for the initial conditions. The first one, the first objective, the most important reason is that the initial and final conditions must be known to evaluate the. So the first objective of the studying the initial conditions, it is needed to evaluate the arbitrary constants that appears in the general solution of the differential equations. The second objective, the initial conditions give knowledge of the behavior of the circuit elements at the instant of switching. The third objective, the final conditions give knowledge of the behavior of the circuit elements after settling of the circuit at t is equals to infinity. When switch is maintained for a long interval of time, it is called as a final conditions. So because of these three, we need to study the initial and final conditions. These three are the objectives of study of the initial conditions. All right. So the first element, initial conditions in the elements, that should be initial and final conditions in the element, that will be discussed now. Initial and final conditions in elements, that is L, C and R. Okay, first we do see the inductor. Initial and final conditions in the inductor. So let us draw the simple diagram. A voltage source, it is connected to an inductor and switch is represented in this fashion. It is t is equals to 0. It is what the voltage V, it is what an inductor L. All right. The first thing is explain that the switch status. What is that switch? When switch is operated. Okay, before switching, write two conditions. Before switching, switch was open. After switching, switch is closed. Is that right? So this is the meaning of this symbol. Before switching, before operating this switch, it was open. After operating, it will be closed. Okay, so the things what we do measure in this case, they are called as t is equals to 0 minus values. The things which we do calculate in this region, they are called as t is equals to 0 plus. Okay, we know the expression for voltage stored in an inductor. Expression for voltage stored in an inductor equals to voltage across inductor is equals to L into dIL by dt. Call this as equation number 1. We know it. It is a standard formula. Voltage across an inductor is given by L into differentiation of current flowing through it. And always L is measured in terms of Henry, voltage is in terms of volt, and current in terms of amperes. Then, if the current flowing in an inductor and it is DC, I repeat, if the current flowing through an inductor and it is a DC value, then what is current flowing through the inductor? That will be 0, because DC, it means there is no variation, it is a constant value. It is a constant value. So what is differentiation of constant? That is equals to 0. So in case of DC power supply, so what is voltage drop across an inductor? It is 0. Keep that point in your mind. When the supply voltage is DC, current through an inductor will be 0, because DC value will be constant, differentiation of constant is 0, 0 into L, it is 0, voltage across an inductor when the supply voltage is DC, it is 0. Alright. Next, what we do say? Let us calculate current through an inductor here. So from this equation, can I calculate I? I is equals to 1 by L into integration of minus infinity to t, that is equals to V into dt. Means apply integration on both sides. Apply integration on both sides. So this integration and differentiation will be cancelled. What is remaining here? Integration of VL divided by 1 by L. So that, let us take this value. The limits are varying from before switching till switching. It is what time interval t. What is the meaning of this minus infinity? So if this is the reference time interval t is equals to 0, so these are called as t0 plus, and this is called as plus infinity. These are called as t0 minus, and this is called as t is equals to minus infinity. Means the previous state maintained for a long period of time. After switching, that time interval, that status is maintained for a long time interval. Alright? So if you want, you can say it as VL. Now, what I will do, I is equals to 1 by L. Can we write this integration? Can we write these limits from minus infinity to 0 minus VL into dt plus 0 minus to t VL into dt. So I can replace this value. Is it nothing but an expression for current I? But I write this value as I0 minus. You can see here, it is what? T0 minus and 0 minus. That value is nothing but in this region value. So that it is nothing but an I value, but that I is before switching value. That before switching value can be represented as I0 minus. And this value, write it as it is, 0 minus t VL into dt. Now, so this I can also be written as I of t, that is equals to I of 0 minus plus 0 t into VL into dt. In this expression, replace t by 0 plus. Wherever you do find t is equals to 0, t, that should be replaced by 0 plus, so that I 0 plus, I 0 minus, 0 plus, 0 minus VL into dt. So that I will write here 0 plus, that is equals to I 0 plus 0. I have replaced this as 0 because you can see here this is the time interval from 0 minus to 0 plus. You can see here, consider this as a graph. It has a reference t is equals to 0. It is what plus infinity, it is what minus infinity. So this is a time interval immediately switching and immediately before and after switching. What is the time interval? It is in terms of micro or nanoseconds. In that nanoseconds, so the voltage will be constant. So what is integration of constant? That will be 0. Or else you can say that it at that time interval, so the voltage will be 0. Immediately before and after switching, the voltage across an inductor is 0, so that this value can be treated as a 0. So the what is final expression? 0 plus, that is equals to 0 minus. So the meaning of this is current through an inductor will be same before and after switching. One more definition. So the inductor will not support instantaneous change of the current flowing through it. I repeat here. Instantaneous change of current is not allowed in inductor, or else the current through an inductor is the same before switching and after switching. You should keep the point in your mind. Okay, so the question may be asked as, show that the current through an inductor will not be changed instantaneously. The current through an inductor will not be changed instantaneously. At that time, it should be the derivation. Is that okay? So the key point in inductor is what here? Current through an inductor will not be changed immediately. Before and after switching, current remains the same in an inductor. All right, good. You will see the next capacitor. So this is the switch and this is the capacitor. So this is what is equals to 0. Plus minus, it is volt and it is C. Okay. Same thing, write a few words about switching. Before switching, before switching, switch was open. After switching, switch is closed. All right, we know that the standard expression for the capacitor, current through a capacitor is given by dV by dt. Call this as equation number 1. Or else you can use here the term T. All right. Okay. So integrate this equation, apply integration on both sides. What happens? It is what integration of IC of t, C into integration and differentiations will be cancelled. We will get Vc. So it can be written as Vc of t. So even it can be represented as Vc of t. Both are one and the same. That is equals to 1 by C into integration of IC of t, So limits from minus infinity to t, call this as equation number 2. So from equation number 2, I can change the limits. Vc of t equals to 1 by c. So minus infinity to 0 minus, that is equals to IC of t plus 0 minus to t IC of t. Alright. So Vc of t equals to 1 by c. So I can write this complete term as Vc of 0 minus. You can see here. So this is what the values, if it is our reference, so it is nothing but V0 minus, time interval at minus infinity, all these values. This is the portion, so that the values which are calculated in this portion all are represented with minus signs. So that this is current flowing through a capacitor, and we have represented, they are before switching. The current flowing through a capacitor before switching, this is the meaning here. Plus, write it as it is, IC of t. Alright, so replace t by 0 plus in this equation. Wherever you do find t, replace it by 0 plus. Vc 0 plus, that is equals to Vc 0 minus plus. So this is the limit, it should be replaced by Vc 0 plus, okay. It is what? IC 0 plus. Okay, you can see here, this value is 0 here. This value is 0. 0 plus, that is equals to V0 plus, 0 minus. This value is 0 because we don't find any current immediately with a small amount of time interval. You can see here 0 minus and 0 plus. Can you say that very small amount of time interval? In that time interval, we don't find any current through an inductor. So that it is 0. If it is 0 means the complete integration will be 0. So that Vc 0 plus equals to Vc 0 minus. The meaning of this is the voltage across a capacitor before and after switching will be same. I repeat, before and after switching, the voltage across a capacitor will be same, or else the one more definition. So the capacitor doesn't support the instantaneous change of the voltage across it. Instantaneous voltage change will not be supported by the capacitor, or else before and after switching, the voltage across an inductor will be same. Keep that point in your mind. Am I okay? Is that okay? Two conclusions after the discussion. They are: inductor will not support instantaneous current change through it. Meaning of this is, immediately before and after switching, current through an inductor will be same. I0 plus equals to I0 minus. In a capacitor, immediately before and after switching, voltage will be same. That means voltage will not support the instantaneous voltage change across it. These two are the discussions. These two are the conclusions from the today's discussion. Is that okay? So in next class we will see the final conditions, what will happen. Alright. So thank you. Have a nice time.